Now, Kira, you were in my last class. If you do happen to listen to that YouTube video, you'll find the last 30 minutes or so is blank because I forgot to stop the recording. So it has some extra time at the end, and you'll see me come in and start setting up this class and then suddenly realize, whoops, I never ended the last one. So anyway, I don't know if anyone's going out to check that or not, but they'll usually stop looking when everything is over, I guess. All right, if there are no questions or concerns, issues, problems, anything else, then we're in Chapter 2, our first order differential equations, in Section 2.3, linear equations, and we're basically just about through with this section, 2.3, and then we'll move on to 2.4. We're on page, at least my mark indicated we're on page 61, and we were talking about the error function and the complementary error function, okay? And I know there's huge use for this in things like statistics and other things like that, but a lot of the rest of the time it just doesn't seem to be all that, I hate to say this, pertinent. But let's see if we can wrap up with one example here. If we're solving an initial value problem, that would be like number 6 way back there, and recognize that indefinite integral on the right hand side of 5 would lead to a non-elementary integral, such as the error function, stuff like that. Then, as we saw in example 5, section 2.2, it's convenient to use instead definite integration over an integral from x0 to x. Okay, now I don't even remember specifically what they're talking about there, but I know that's done. The last example illustrates that this procedure automatically incorporates the initial condition x of 0 in the solution of a differential equation. In other words, we do not have to solve for a constant c in the general solution, which sounds like a good idea. If you have an initial condition, you don't have that. So here we are. Let's solve the initial value problem. dy dx minus 2xy is equal to 2. Okay? Initial condition, when x equals 0, y is equal to 1. Y of 0 is equal to 1. Now, just looking at this, this is not a separable equation. Okay? Going to have to use the linear principle. It is set up perfectly for linear. Coefficient of 1 here. Your p of x would be minus 2x, and your f of x is 2. Okay? So, let's go to the white page and whiteboard and solve it. Let me make sure there's no one else waiting in the wings that I can see. So let's go to the whiteboard. Okay, let me get my pen now. I've got to move whiteboard stuff around. So I'm going to move this as far up as I can. And let's move the whiteboard as far left and up as we can without losing too much. And then I'm going to move Kira and the rest of us back here to the side so we'll be less in the way. Okay, here's example 7. dy dx minus 2xy is equal to 2 with the initial condition that y at 0 is equal to 1. When x equals 0, y is equal to 1. Okay. Now, let's go back through the steps. First, this is in standard form. Leading coefficient here of your first derivative is 1. That's exactly like we want it. That makes the p of x here to be minus 2x. So your p of x is equal to minus 2x. No y dependence there. Linear form. We don't mess. For some reason this pen will not write the x well. Okay, now it's pretty ugly. What do we do with that? We integrate it. The integral of minus 2x dx will be minus x squared. We don't put a plus c with that. Just do the integral, minus x squared. What do we do with that? We make that the exponent of the e. Okay, what do we do with that? That is our integrating factor mu as a function of x and x alone. Okay, so we multiply that by each term. So that would be e to the minus x squared dy dx minus 2x e to the minus x squared y is equal to 2 e to the minus x squared. Okay, multiplied it by each term. Now this should be, and I believe will be, perfect derivative of d by dx of your integrating factor e to the minus x squared times your y. That's what it should be. Let's check it and make sure it is. It would be first times the derivative of the second, e to the minus x squared dy dx, that checks, times the second, there's the y, times the derivative of the first. The derivative of the first is e to the minus x squared. That's good. We just lost Ryan, I think. Okay. Times the derivative of the inside part minus 2x, and sure, we have it. And he's trying to come back. I don't know. Should we let him back or not? Let's try. Well, I tried to let it. There he is. He's back in. Okay. Did your system boot you out, or did you have to go out for some reason?
I'm just having difficulties. I'm doing a lot of things at once. It was
Yeah.
my fault.
No problem. I was going to say that my system has kicked me out, I'd say 3 times in the last 2 days. Okay, it's been awful. Right in the middle of things, and suddenly Zoom is trying to connect again. I never even knew it when it disconnected. So I was just checking to see if that was happening to you. All right, so we have, I think, confirmed that that the left-hand side is the perfect derivative there, and this is 2e to the minus x squared. That's the right-hand side. Well, if we wrote that in differential form, put the dx over here, and then integrate both sides, the integral of a perfect derivative is just what's inside, e to the minus x squared y. And the integral over here would be 2 times the integral of e to the minus x squared dx. Okay. You take a look at that, or you can multiply both sides by e to the x squared and get y is equal to 2 e to the x squared times the integral of e to the minus x squared dx. Okay. And you could put, if you wanted to, your plus c out here. Okay. But what we're going to do is plug in when x equals 0, y is equal to 1. So let's plug that in. That makes the left-hand side 1 is equal to, when x is equal to 0, 0 squared is 0, e to the 0 is 1, so you have 2 times the integral of x is 0, x squared is 0, minus x squared is 0, e to the 0 is 1. So basically you have 2x plus c. But what is x? X equals 0. So c is equal to 1. Okay? So what we have then is y is equal to 2e to the x squared times the integral of e to the minus x squared dx plus 1. Okay. Now, if you notice this right here, this integral, we've seen something very close to it before. That is very close to the error function. So with that in mind, I'm going to leave it just like this. I'll just mention to you, we have here's James coming in. Good deal. So let me mark James here. So we got the top part of the alphabet is covered nicely, all three people here. The bottom part, though, we have neither of those two. So James, we're working on example 7. We're in chapter 2, first order differential equations, section 2.3, linear equations, and we're doing example 7 on page 61. And we just had gotten to this form here. And we have y is equal to e to the, okay, I'm sorry, I left off a parentheses, I think. If I can get my pen, I'm using the wrong side of my pen. This was like this. So this should have been like that, I think. And then we could carry this to be y is equal to 2e to the x squared plus the integral of, or 2e to the x squared times the integral of e to the minus x squared dx. Okay. Well, no. I don't know. We were agreeing so closely, and now I have a 2 where they don't have a 2. I think they've just done their substitution differently from me. No, I'm sorry. Okay, I'm sorry. I see what happened. This 2 was inside the parentheses, not outside. Okay, so that has it. Okay, yeah. So y is equal to e to the x squared plus 2e to the x squared times the integral. Now they put the limits on here, 0 to x of e to the minus t squared dt. And you can do that if you want to. 0 here, x here, and then make that a t squared and a dt. That's what they did. Now, this part right here looks very close to the error function. So let's see if we can write that in. Y is equal to e to the x squared. Okay. Let me clean this up too. That's where that came from. And anyway, if you go back to the error function, how this thing right here differs from that, we've got the 2, we've got the integral, and we've got the e to the minus t squared dt. So everything's good except the root pi. Okay, so what we're going to do here, e to the x squared plus, and we're going to, and that's divided by root pi, so we're going to multiply the square root of pi times e to the x squared, and then we'll divide by root pi with the 2, and this would then be the error function, ERF of x. Okay, yeah, and that, I think, gives us the answer. And then they factored out the e to the x squared, which I couldn't figure out why they were carrying them around that far anyway. I would have left this factored out way back here, but they multiplied through and then pull it out again. So e to the x squared times 1 plus the root pi e to the ERF, error function of x. Okay, and that's pretty much how they leave it. Y is equal to e to the x squared times 1 plus the square root of pi times the error function of that. Now, they use a computer algebra system to graph that, and all that mess that you see there comes out a pretty simple graph right there. That's it. And you see it does pass through the point x equals 0, y is equal to 1. The error function would be a series, a family of curves like that. That's the one that passes through the point in question. Okay. Now, what's that used for? What comes out in graphs like this? I don't have a clue. Okay, but they did want to do at least one problem with that. Then they have a blurb on use of computer algebra systems like Mathematica and Maple, which they use to do their graph, and you can read that if you would like. I don't have access to that, so I'm not going to spend any time on it. Now, page 62 is the last page in the section, and it's the remarks page, which usually I tend to ignore because they can take incredible amounts of time to deal with. But they do have some fairly interesting things there. And I think I'm going to clear the screen and, well, wait, let's just go to the board since we're not going to do anything with it. Well, we might, but let's go back to the board here. And by the way, there was the example 7. I'm going to move y'all out of the way again. Ryan, you're in the way. Okay. Let's scoot on down. This is how that problem was set up and worked. And that's the answer we got. And to talk about use of computers. Now here's the remarks. Now, here's the interesting thing. Occasionally a first order differential equation is not linear in one variable, but is linear in the other. So if you were to do this one, the differential equation dy dx is equal to 1 over x plus y squared. That's obviously not linear in y. Number one, y is in the denominator, it shouldn't be there, and it's squared, it shouldn't be there. But if you reciprocated both sides and made dx dy is equal to x squared plus y squared, hey, wait a minute. Move the x over with the dx dy, you have dx dy minus x is equal to y squared. Hey, that's linear in x, not in y, but it's linear in x. And this is what you get when you do that. That's exactly what I said arrange it this way. And then you can go to town and solve that problem. Okay, that's linear in X, but not in Y. And then your integrating factor, your coefficient here, your P of X is -1. The integral of P of X would be minus X. E to the minus X would be your, it's dy then. P of Y would be -1. Integral of that would be integral of -1 dy. That integral would be minus y, okay? And e to the minus y would be your integrating factor. You multiply on this side, and that side, and sure enough, you would get something that looked like that. That would be your solution, okay? And that expression is an implicit solution of that first equation. Now, you can't solve this in terms of y. It won't work. I mean, you can't do it. It's not solvable. But it is a function. X is a function of y. You can do that. Now, that then leads them to talk about some other stuff here. And part of that other stuff is mathematicians have adopted as their own certain words from engineering, and sometimes they agree and sometimes they maybe not quite so much. The term transient, used earlier, is one of those terms, okay? E to the minus y squared, minus y would be a transient term. E to the y would not be a transient term. That explodes for large values of y. So this one doesn't have one of those. In further discussions, the word input and output will occasionally pop up. That's no one new coming in the courses. I think I just happened to hit the bar down at the bottom. Okay. So sometimes the function on the right hand side, in this case would have been your y squared, would be the input or driving function. Usually it's y of x, but you know, whatever, of the differential equation. And the thing on the right hand is input or driving function, and then the y of x, your solution, would be the output or response function. Now there's another thing that's mentioned here, and I'm not going to do it because we're going to do anything with it. The term special functions mentioned in conjunction with the error function also implies to the sine integral function, and then there's another one called the Fresnel sine integral function, okay? And that is going to be introduced in problems 47 and 48 of this section coming up. I think that's in the discussion. No, it's not in the discussion part. That's actually other. Special functions actually is a well-defined branch of mathematics, and more special functions are studied in 6.4. We're not going to get there, okay? Now, why do I mention this? You might find who or what fields use a sine integral function anyway. What's it used for? What is its value? What does it add to your tool belt by having that in there? And then, not only that, who in the world was Fresnel, okay? And how did he adapt the sine integral function to a special sine integral, or what? So I'll let you look at that and see if there's anything you might be interested in. This is sort of a big hint to suggest please get working on your research papers. We're getting awfully close to midterm. Just about always the second half of a term is way busier than the first half, so good idea to go and knock those research papers out of the way now as soon as you can. Remember, if you get it into me today, it's the last day to get your 3 bonus points. Starting tomorrow, it'll only be 2 bonus points for the month of October. So if you can get it to me today, that will give you that extra bonus point. Okay. Now, exercise set 2.3. Do any of the odds 1 through 23, and there they all are listed there. If you have the answer in the back of the book, try those exercises, or as many of them as you need to convince yourself, yeah, I've got this down. Then 25 through 35, if any of those that are in the back of the book, go for those, okay? And then any of the odds 37 or 39, any of those in the back of the book, those are piecewise functions. We did one like that in class. I'm sorry, 37 or 39. And then top of the next column, which I'm trying to get to now, gives you 41. Okay, try to do 41. If this answer's in the back of the book, it's another piecewise defined function. But this time, it's your p of x is a piecewise defined function, which is another sort of issue there. 43 should be in the back of the book, so try that if you can, and 45 also. Okay? Then remember the sine integral function, 47, and you don't need to do 48, but that's where the fractional sine integral function is mentioned. After that, there are discussion problems. If any of those have answers in the back of the book, you can go look through those as well. Most of the time, the discussion problems do not, but check them out and see if they do. Any questions on 2.3, linear equations? This is not linear equations like you had back in Math 100 or something like that, or even 098. These are linear differential equations, so quite a different bag of worms. Okay, there are some mention here made of radioactive decay series, heart pacemakers, things like that. If you find those are interesting topics, you might want to follow those up as potential paper topics. So now we move to 2.4, exact equations. Now that sounds like a rather nebulous term there. Are all equations exact? Well, that's not what we're talking about here. Now, for exact equations, they're not always written this way, but you always wind up writing them this way. If you have a simple first order differential equation like this, y dx plus x dy is equal to 0, you know you can solve that by separation of variables. Subtract either one of them from the other side, and now you have y dx is equal to minus x dy, and then divide both sides by x and divide both sides by y, and you get a separable equation. Okay, it's separable, it's also linear. Okay, I would put the dy in front and then divide by dx, and you have dy dx is equal to y over x, or 1 over x times y, or plus 1 over x times y is equal to 0. That's certainly a linear equation. Okay, but there's another way we could solve that one, recognizing that the expression on the left hand side of the equality is a differential of some function f of xy is equal to xy. Okay, the product x times y. Because if you were to write that in differential, take a derivative of that, then a derivative of the right hand side anyway, d of xy would be x times derivative of y plus y times derivative of x, and that's exactly what you've got here. So that means if you can write an equation in the form to make it a perfect derivative of something, well, now let's remember this thing here is equal to 0. So the derivative of xy has to be a constant, because that has to be 0, so the product of x times y is a constant. Okay, in this section we'll examine first order equations written in this differential form. Some combinations of x and y, m of xy times dx plus n of xy dy is equal to 0. Now notice a key here, it has to equal 0, not some other function or anything else. But you have, when you write this in differential form, you have a function of x and y here, another function of x and y here, and that combination is equal to 0. Now, there is a test, and it's a pretty simple test that to applying a test to m and n, these coefficient functions here, you can determine whether this is indeed a differential of a function f of xy. If the answer is yes, we can construct f by partial integration. Okay? Now, remember way back at the beginning, we said there's two trying to remember what we called them now. Order was what the derivative it was. Linearity is that, what we've just been talking about. This is classification by type. That's what it was called, type. Two types of differential equations: ordinary differential equations and partial differential equations. Okay? This course is not doing partial differential equations. These are ordinary differential equations. You only have dx, dy, no partial of x, no curly d's. Okay. However, I told you at the time that didn't mean we wouldn't be doing some partials. Now I know that 2 of the 3 of you are in Cal 3 right now, and I know that you haven't gotten to partial derivatives yet. Ryan has already done Cal 3, right? I think he has. So he should be familiar with partial derivatives. We are going to need partial differentiation to do exact equations. It's not a partial differential equation, but we're going to be using partial derivatives to solve the ordinary differential equation. Okay, so here's something that you haven't had before, but I think you'll find it's a pretty easy concept. Okay, now if you have a function z is equal to some function of x and y, it's a function of two variables with continuous first partial derivatives. Okay, we'll talk about what those are in a minute. In some region R of the xy plane, okay, something in the xy plane, some region there in the xy plane, then recall that from calculus that the differential, if you take a derivative of this, d of z, that's what we're doing here, is the partial of f with respect to x times dx plus the partial of f with respect to y dy. Okay, that's just, you haven't gotten there yet, but you're going to get there hopefully in Cal 3. Okay, but this is taking a differential of this. You have a single variable, single dependent variable based on two independent variables. They're independent from each other and both independent of z. Okay, now when you have such a case, you can't take a normal derivative. You take a partial first with respect to x, multiply that by dx, then do the partial of that function f with respect to y, and multiply it by the differential dy. So this is a characteristic. Anytime you have a function that can be written like this, you know this is what it boils down to. It's differential dz is equal to partial of f with respect to x dx plus partial of f with respect to y dy. Now, in the special case where this f of xy is a constant. C is a constant. Then, if you take this side and you know that this z is a constant, the derivative of z, or the differential of z, has to be 0. So here we are back at the form we were talking about before. Some function of f of x, some function of x and y dx plus some other function of x and y dy is equal to 0. In other words, you wind up with a one parameter system, because this is first order differential equation. dz, dx, dy. You have one first order differential equation. So you get a one parameter family of solutions. That is your family of solutions. F of xy is equal to c. There is your one parameter, c. Okay, then we can generate a first order differential equation by computing the differential of both sides of that equality. Okay, so let's say this is what we have. X squared minus 5xy plus y cubed is equal to some constant c. Now we're doing things backward from what we will be doing, but this is just to give you an idea of how this works. Okay, now if you're doing a well, I'm going blank on the word for it, implicit differentiation of this equation here. Okay, implicit differentiation. Let's go to our whiteboard, and I'm going to have to move y'all around a bit. Sorry to keep juggling you. Okay, let's go back to the whiteboard and move Kara down here to the side. Okay, now what did I do? There it is. Okay, all right, for me to clear the screen. Okay, here was what they gave us. I'm going to have to get my book in my lap because it's too hard to read from the side there. Here we have an equation. X squared minus 5xy plus 3y plus y cubed is equal to some constant c. Now this is backward from what we will be doing, but this is just to give you a flavor. Okay, if we do an implicit differentiation of this in differential form, not derivatives, but in differential form, the partial of this, the derivative of this will be 2x dx. This is in differential form. Now this will be minus 5. Now you have a product rule here, so this will be a x dy minus 5 y dx. Okay, because the product rule is first times the root of the second plus the second times the root of the first. Okay, then the third one would be the fourth term produces plus 3y squared dy is equal, and when you take the derivative of this, you get a 0. Okay, now let's get all the dx's together and all the dy's together. The two dx terms are these, and that will give you 2x minus 5y dx. I'm going to put a plus here, okay, and then I'm going to lead off with this one, 3y squared minus 5x, that would be these two, times dy is equal to 0. Okay, notice what we have here. Some function of x and y, m of xy dx, plus n of xy dy. This is a function of x and y dy, and that is equal to 0. Okay? Now, anytime you have a function like this that is equal to a constant, it's any kind of, I can't get my pen to show up. There it is. Anything like this, that when you take your kind of implicit differentiation, but in differential form, do it out and then split it like this, you have now gotten it into a differential form where you have functions of x and y dx plus a function of x and y dy is equal to 0. Okay, that's what we're wanting to go. Now, let's go back to the book. If I can get my pen. Ah, there, it's somewhere down there now. Okay, here we go. Let's just make sure nobody else is waiting. They're not. And then go back down here and go back to the book. Okay. And now I'm going to move y'all again. Ryan, you're in the way again. There we go. Okay, we've just done this. X squared plus 5 minus 5xy plus y cubed equals c. That equation, function of x and y that's equal to a constant, gives you a first order differential equation that looks like this. Some function of x and y times dx plus some other function of x and y dy is equal to 0. Now, they say here, of course, not every first order differential equation written in differential form like this corresponds to a differential equation, to a differential of an equation like this. Okay? It won't always happen that way. We just picked an equation like this and made it look like this. But not every one like this you can make to look like that. You can do it one way, but you can't do it the other. So for our purposes, it's more important to turn to the foregoing example around. That's what I said, we're doing it backwards there. Namely, if you're given a first order differential equation like this, see if you can come up with an expression like this that will break that down for you. Okay? No, I'm sorry. If you have an equation that looks like this, see if you can find the function that gives you your solution. Okay? Now, is there then an implicit solution of that? The answer after this definition. All right, let's look at the definition. This is the definition of an exact equation. Okay, I think we just lost James. Okay, he kind of disappeared on me. Let's see if he's trying to get back in. Nope, it's just the three of us now. I bet you he'll be coming back in just a minute. While we're waiting, I'm not really waiting, but let me pause just a moment and get something to drink, because I've been talking almost nonstop since 10 o'clock this morning. The throat is running out. All right. A differential equation that can be written like this, m of xy dx plus n of xy dy, is an exact differential in a region R of the xy plane if it corresponds to the differential of some function fy defined in that region R. And the first order differential equation of this form, m of xy dx plus n of xy dy equals 0, is said to be an exact equation if the expression on the left hand side is an exact differential. If it is an exact differential of some function f of xy. Now, here's another example. Let's go back to the whiteboard. Okay. And I would say let's leave it, but let's go on and clear that out of the way. Now, I think I also move Kara out of the way. Okay. Okay. Now, here's a differential. X squared y cubed dx plus x cubed y squared dy is equal to 0. Now, they're claiming this is exact. And here's how we know that. Looking at that one, we can almost guess what the function would be. Your f of xy would be something on the order of, oh, here comes James back in. I knew, or I had a feeling he was going to be trying to come back in. Let's see if anyone else is waiting. I think it's just James. All right. Glad you made it back, James.
Yeah, I don't know what happened.
Yeah, like I said earlier, that's happened to me at least 3 times this week. I'll be talking along, teaching along, and all of a sudden, Zoom is connecting again. I thought, when did it disconnect, you know? So, yeah. I don't know if it's something with the internet. I don't think there's anything in the atmosphere right now. I look outside, I see perfectly blue skies. Absolutely no disturbance there. There is a bit of wind, and that's maybe normal for this time of year, but goodness gracious, I see no reason there should be interruptions. But earlier this week, usually those things happen when I had 5 bars of internet, and for some reason it was telling me the internet was unstable. There's something goofy. I don't know what it is. Okay. But we can almost look at this. This is on page 80 or 65, just below the definition for an exact equation there. Definition 2.4.1. Okay. Now, we can almost look at this and say, what if our function was something like x cubed y cubed? Okay. What if this was our function? Okay, f of xy was equal to that. Okay, now remember, okay, if we were doing a differential of that, that's a product rule, and that would be, so we'll say d of f, okay, and it really doesn't matter which one we do. We're going to do it in differential form. D of f would be 3x squared y cubed dx Oh, I thought I had my eraser. It says I have my eraser. There we go. Okay. This is going squirrely now. Plus, and then you did it with respect to y, 3x cubed y squared dy. That would be your the differential of f. Okay, you do it first with x and then with y, and you see this is exactly what we've got up here except for a 1/3. So if you put a 1/3 in here, then the 3's would cancel out with the 3 in the denominator, and you would have exactly that form. Now that one you can almost look at and guess. Okay, we don't want to be guessing, so we're going to come up with a better technique than this. Okay, and here's what the technique is. This is what we call our m of xy. That's a capital M. And this is what we call our n of xy. They just arbitrarily chose those names. Now here is where we're going to hit our partial derivatives. What we're going to do is take the partial derivative of m with respect to the other variable, with respect to y. Okay, and this is your m, x squared y cubed. So what we're doing is the partial derivative with respect to y of x squared y cubed. Okay, so let me show you how to do this. To take a partial of a function that has two independent variables. If you only have one independent variable, you're only taking an ordinary derivative. It's only when you have two or more independent variables do you take partials. So here's what we do. We're taking with respect to y right here. So therefore the only variable we treat x as if it's a constant and only treat y. So that derivative would be, partial derivative would be 3x squared y squared. Because you're only taking with respect to y, you treat the x squared as if it's a constant. Okay? Now, that's taking the partial of m with respect to y. We also take the partial of n with respect to x, because that is the opposite variable. Okay, I'm sorry folks, my head is closing up so badly it's hard to think. I'm going to have to pop a little bit of caffeination, carbonation, something. I hope that will help. Sometimes it does, sometimes it has no effect. Now, this time we're taking the partial of n with respect to x, because that was the other variable from here. So this is the partial with respect to x of x cubed y squared. That was your n function. That's x cubed I said, y squared I said, and wrote them differently. I don't know what's going on. That's your n of xy. Okay, again, since you're taking the partial with respect to x, you treat the y squared as if that's a constant. So this would be partial with respect to x would be 3x squared times y squared. Y squared is just a constant. Well, looky here. These two opposite partials of each other, of each of the two different things, are equal to each other. And that's how we can tell that that is a perfect differential. If the two partials taken with respect to the opposite variables are equal to each other, that gives us our answer. Okay? Now, this next theorem shows this is not merely a coincidence. So let's go back to the book. It means I'm going to have to move everybody around again. Okay. All right. So let me move Ryan back up here. Okay. So let's get on down to this theorem. That's what we just showed here. They turned out being the same partials of each other. Okay. And here's why it says this is no coincidence. Criteria for an exact differential. if you have an m of xy and n of xy are both continuous functions and have continuous first partial derivatives. In some rectangular region R, a is less than x is less than b, c is less than y is less than d. Okay? Then a necessary and sufficient condition that m of xy dx and n of xy dy plus n of xy dy be an exact differential is that the partial of m with respect to the other variable y is equal to the partial of n with respect to its opposite variable x. Okay, now they go through some of the proof for the necessity part. Okay, remember we said necessary and sufficient. Here is part of the necessary. Now I'm not going to go into this in gory detail, but let's just take at least a cursory glance of it. Let me get this hot book out of my lap. Okay, for simplicity, let's assume that your m of xy and the n of xy have continuous first partial derivatives for all xy, not just in some special region. Now, if the expression m of xy dx and n of xy dy is exact, then there exists some function f such that for all x's in the region R, which is now all real numbers, x and y, excuse me, m of xy dx plus n of xy dy is equal, it has to be equal to, okay, there has to be some function f such that the partial of f with respect to x dx is equal to plus the partial of f with respect to y dy. In other words, this m of xy must be the partial of f with respect to x, and the n of xy must be the partial of f with respect to y. Okay, and that's what they're saying here. Now, if you were to take the partial of this m with respect to the other variable y, and do this, you get m, the second partial of f with respect to y second and with respect to x first, and you see that that's exactly what you get if you do the partial with respect to x of this n, which is the partial of f with respect to y. Now this is something you haven't had yet, or at least two of the three of you haven't had yet because you're still in Cal 3. The mixed partials, if you have continuous functions, then the mixed partials have to be equal. And we just lost James again, sorry. Okay, and he's now trying to get back in, and I can't get him when we are up there. So let me see if I can move this and admit him here. Okay. Welcome back, James. Well, he's still connecting to audio.
I'm here.
I know. I saw you leave and saw you come back. Okay. All right. The reason this is true is that the second partial, the mixed partial of a function, if everything's continuous, okay, the f is continuous, it's mixed partial, no matter which order you do it. First partial with respect to y, then with x, or first with respect to x and then with y. Doesn't matter the order, these two are the same, as long as the functions are continuous. Okay? Now the equality of mixed partials, that's what they call them, one with x, one with y, is a consequence of the continuity of the first partial derivative of m of x and m of xy and n of xy. The sufficiency part of the theorem consists of showing there is a function f for which that is the only one, okay, and the construction of the function f actually reflects the basic procedure for solving exact equations, which is what we're going to get into now, our method of solution. Now, as always, this gets bogged down easily, okay? But just step back from it. Don't try to memorize it. Just sort of get the concept down, and then that's how you'll do your problems. You won't plug and chug, you chug and plug, I guess. You go the other way. Okay, so let's say we have an equation in differential form. M of xy dx plus n of xy dy is equal to 0. Now, the first thing you always do, make sure the partial of m with respect to the other variable y is equal to partial of n with respect to x. You have to do that partial differentiation. If that holds, if that equality holds, then we know, because this is our assumption, that there is some function out there, f of xy, equal to a constant. Okay, equal to a constant, because this is, when you take the derivative of it, it becomes 0. That f of xy equal to a constant, the partial of that with respect to x has to be that m of xy. That's how we set this thing up. That's what we've been doing all along. Okay, so guess what we're going to do? We're going to integrate this. In other words, write this in differential form, right? Partial of f with respect to x equal m of xy, and then we're going to change that curly d to a d and say dx. Now that may not seem like it's fair, but it's okay to do. Okay, and if you can integrate that f, and we don't know what f is, so that would just integrating a derivative just gives you f of xy. If you can integrate this with respect to x, remember that's what you pulled over here, then remember we're only integrating with respect to x. Again, we treat the y's that are in here just as if they're constants. Don't mess with them. Just treat them like constants and only do the integration with respect to x. Then normally we do that integration and do plus c. But guess what? We just don't have a c anymore. We could have some function of y alone. Now that may be a constant, but it could have some y dependence, because you see we treated y as a constant here. So our general form would be you'd have some constant function left over, and that would be a function of y. Not x, because x you integrated out, only the y. Where the arbitrary function g of y is the so-called constant of integration, because you're integrating only with respect to x, so that constant, you might call it, would be with respect to y. Okay. All right. I was just checking my time. I was afraid I'd gone over, but now I see I've misread the time. Okay, so this is your f of xy. Now, what we're going to do is differentiate this with respect to y. Okay, because the partial of f with respect to y should be your n of x. So you do that. Take the partial of this with respect to y. Now this is something, it's no longer an integral. You've already evaluated the integral. We just don't know what it is. And this is just a function of y, so that's going to be a derivative of g. Okay, that's what you get here. So you take whatever this came out being, they're just representing it by that integral. You take the partial of that with respect to y, add that to g prime, and set that equal to n of x dx. Okay, and then solve and figure out what that g prime is. And you do that by subtracting this part from that part. Okay, now all right, remember this is just some function of x and y. This is some function of x and y. Over here you only got a function of y. So you're hoping, and it better work out this way, that any x dependence is going to neutralize itself here. Okay, and when you take the derivative of this with respect to y, you'll lose the x dependencies there, and you're going to come up with just some function of y. Now, the implicit solution of that equation then is that f of xy is equal to c. Now, it seems like, hey, where did that come from here? Okay, we'll come back to it in a minute. Some observational order. First, it is important to realize the expression, this thing right here, is independent of x. Because there's no x over here, there can't be an x in there. So when you do all your stuff there, your x terms should have disappeared. Okay, I think that was just me hitting it. Let me just make sure there's no one else trying to come in. No. Okay. Yuck. Now, all right. Secondly, we could just as well start the preceding by doing this, assuming the partial of f with respect to y is n of xy, rather than partial of f with respect to x was m of xy. You could have started on the other side and worked the other way. Then your constant of integration would have been a function of x, not of y. Then you take the derivative of that, well, the partial of this with respect to y, and made this your m, and then subtract that. So you could have gone the completely different route, come around with the same thing. None of those formulas should be memorized. Do the procedure, don't memorize the formulas. Now, the question is, can we do example 1 in 3 minutes? I don't know that we can, but we can give it a shot. So let's give it a shot. Let's go to our whiteboard. If I can find my cursor, there it is. Let's go to the whiteboard. And we'll at least get started. We probably, okay, got to move y'all out of the way again. So let me get you there. Let's clear the slide and let's start. This is example 1 on page 67. Here's what we're trying to solve. 2xy dx plus x squared minus 1 dy is equal to 0. Okay. Now, first thing we do, we identify your m of xy is equal to this thing, 2xy. And that makes n of xy, and this funny is only a function of y of x, but we'll leave the y in there for now, is equal to x squared minus 1. Okay. First thing we've got to do is verify that this is an exact differential. Okay? And how do you do that? You take the partial of m with respect to the opposite variable y. And when you do that, treat x as a constant. The partial of 2xy with respect to y would just be 2x, because you're only taking derivative with respect to y. Let's do the same thing over here. Partial of n with respect to x, that's this one, the opposite variable here. Well, that's pretty obvious to be 2x. Those are indeed the same, so we can proceed. Except we don't have time to proceed. So all we got to do was verify this will work. So what we'll do next time, if I can find my pencil here, I've had it before, it got scooted way back. We will begin, and somewhere here I should have my eraser also, and here I found it, I think. Let me erase my mark from last time I taught the course and mark here. So we'll be starting on the second part of example 1. We haven't done enough for any new homework exercises here, but we will finish this next time. Okay? Now just to look ahead, folks, we're finishing 2.4 probably next time. We'll do 2.5 after that. Then we'll look at a numerical method, and that will be it. So it could be as early as late next week. More than likely the following week we'll be ready for your second test, which means you need to be working on that first test. Now I know 2 of you are in 3 of my classes and you have a lot of tests out there. Please make progress on every front that you can, okay, because it's going to be just maybe about 2 weeks we'll have the second test. Be great to have your first test turned in by then. Okay, any questions? All right, if there are no questions, I'm going to stop sharing. If I can find my pen here, there it is. So I'm going to stop the sharing, and unless there's some questions, I'm going to end the meeting. So we'll see 2 of you tomorrow, and Ryan, we'll see you next Monday. Okay, so y'all have a good weekend. Make sure it's a safe weekend, and of course working on differential equations will make it a fantastic weekend. Research papers, that kind of stuff, please be making progress. I'm going to be doing my best to catch up with my grading, things that James was asking about before. I'll try to get that done. So any last thoughts, parting shots before I end the meeting for us all? Okay. Then here we go. Take care. See you tomorrow or Monday. Bye-bye.